How's everyone doing? All right. All right. It's good to see everyone here. It's good to see everyone. Give everyone just a little bit more time to settle in. I have made some pretty pictures for us. I am pretty excited. I'm very interested to know how you guys like this type of content. So let me know. And this is kind of like what we did with the databases, except this is going to be less code. This just, well, by less code, I mean there is no code for this portion. Not next week, but the week after, we're going to start on our discussions around how systems reach consensus, and this is like a kind of a primer to that. It's information you probably want to know before jumping into that. So yeah. Let me know how that will have code, whereas this one doesn't have code. I expect roughly for this to take about an hour. So this is 2 days. I'm also going to do this on Saturday. This is a 2-part. If you're wondering, the 2 parts are this. Basically, I want to stress the importance of CAP theorem, and then I want to tell you why you don't need to worry about CAP theorem, and it's kind of bad. I think it's actually both good and bad. So I can convince yourself either way. I think it's really important to know and to understand at a decent level, and in that you'll understand why maybe, not that it's antiquated, but that it doesn't cover everything that's important. It doesn't cover everything that's important, and there's a lot of minutia to it. So I think it's really important. I think we should understand it better. I also think that as we progress, you'll start, after learning CAP and what CAP means and all of that type of stuff, you'll start to learn why it's really important to understand what is important to you, what's important to your application, what your requirements are, and picking a database or a distributed system that supports those requirements. Yeah. So I also have a ton of material on this. So if you have a question and want more for reading on that, why I say any of these things, I have all of that material. So yeah, just let me know. I'm going to be dropping the links as I kind of think that we talk about them. Yeah, I should come up with a better way. I should probably have a command. I was thinking about that, having a command for Twitch for those. But there's a lot of them, so it would kind of be like it would be like throwing up on the page. So I'm not sure that's the best way, but I was trying to compile the people that really influenced me. So I do a lot of reading. So it would be impossible for me to put everything here that, I ever read that influenced my ideas on it or that gave me some knowledge, but I do know some key influential people that really pushed me in certain directions. So those are the ones that I have gotten for you all. All right, well, let's go ahead and get started. I will pause for questions. You're more than welcome to put questions in chat. I'm not going to actively read questions through this first part. Not saying not to ask questions. Please do ask questions. I'm just and ask them as they come up. And I will try to pause at appropriate times to answer those. Okay, so we're going to learn about cap. Now, a lot of the times you're going to see a diagram that looks very much like this. You're going to see a diagram that looks a lot like this. So you're going to see availability, network partitioning, and consistency in effectively a diagram that looks like this. This is what you're going to see. And this is trying to explain simply the problems faced by distributed systems. And so this is cap. Now, where did cap come from? Where do we start to talk about that? Well, that came from a talk that Eric Brewer gave a while ago. Let me pull that up. So this was the talk that Eric Brewer gave and talked about this. Just the problems from the problems that distributed systems have and they have to deal with. So I'm going to post that as a thing so you guys can go check out the original source of that. Now, a couple years later, so that was in 2004 that this came out. A couple years later, I don't remember exactly when. It's probably actually in here, so we're going to go check it out. There was actually Brewer's conjecture was actually put to a theorem and publicized by Nancy and Seth. So you can go read this. This is kind of the proof of the theorem. Now I'm giving you all this context and this content because I want you to understand that cap theorem is correct. It is a theorem. It's not just a theory or an idea. When Brewer first talked about it, it was just an idea. It was just an idea. And very smart person. He knew what he was talking about. This was the proof of it. So you can go through and read the proof of it. I'm also going to link this, what I consider a pretty much easier to understand proof of cap. So go ahead and check that out. It's easier to understand, has some pretty pictures, and it talks about cap theorem with what it means for each one of those things. Now, I will still insist on Saturday that while it is true, there's a lot of reasons why you have to move beyond cap. Now, I would still argue that cap's really important to understand as a base principle, but when you understand it at its base principle, you're going to better understand why it's important to move beyond cap. Anyways, okay. So there's those things. And this is what we get from it. You have availability, you have network partitioning, and you have consistency. And Brewer's conjecture is that you can pick two of any one of these things. But before we pick two of these, we kind of need to understand what these mean. Availability is a vague term. Consistency is a really vague term. And this is actually the definitions that Brewer set forward is what leads you to understand that there's actually more out there that distributed systems have to deal with. And we'll talk more about those. So availability is the idea that if you get a response back, that you have a valid response. So if you can reach the server, it can return a valid response. And consistency is the idea that in Brewer's conjecture, it's more aptly or more aptly considered linearizability. So linearizability is effectively every request that's received by a node that's still active, a non-failure state node, must result in a non-error response. So basically, if the system is still active and working, then you're going to be able to get a correct response. That's kind of the linearizability. Now, I have actually made a graph to try to explain this a little bit better, and we'll get into that. But yeah, that is maybe a difficult way of stating it, but I did bring this up for you guys, so you can go check it out and read more. Linearizability, the correctness condition for concurrent objects. And let me try to explain it a little bit better with a graphic I made. Now, I looked for graphics on this specifically because all of them are terse and hard to understand. You think that you're looking at Egyptian hieroglyphics when you're looking at them, and it takes a while to sit. So I made my own, and I realized that the reason they look that way is it's kind of hard to describe. So mine's not any better, but I'm gonna work on it. Linearizability basically says that you won't have this happen. And what happens here is that you send an update. You update and say that the key for name, or the value for name, is now Sam. And at this point in time. And at this point in time, right here, user B does a GET request, and they hit server 1, and it returns that the name is Sam. User A over here, though, hits here in time, so after. You would expect that they would also get the name as Sam, but server 3 hasn't been updated with that the name is Sam. And so you see that happens later here in time, after this. So they get the old value, Bob. So basically, this is what a lot of people consider eventual consistency, but it's not actually just eventual consistency. You know, a lot of the times the types of databases that try to solve this problem have like a single leader that they read from, and then the followers just are there in case the leader fails for some reason. That's the idea behind it. So this is linearizability. Basically that if two people make a request at the same time or slightly apart and the data hasn't changed, they will get the same response. That's what they're trying to get here and achieve. So this is what CAP means by consistency. So when you're talking about consistency and CAP, Brewer is more talking about linearizability. Now, the reason I stress this so much is a lot of people get confused with ACID CAP. ACID has ACID consistency. ACID has a consistency statement too. That's what the C stands for. And it's ACID is talking about similar stuff, but is generally built on top of CAP. So actually, usually a system that is ACID is built on a system that has picked consistency, a network partition. So that's what consistency means. Okay, that's reasonable. We can kind of understand what consistency means. Anybody have a question so far? Okay, so what is network partition? I think network partition actually is a little bit easier for a lot of people to understand because it's pretty much if you have these three nodes and they're all networked together, something like this and this and this, and yeah, networked like this. And you have a partition. This is what they're talking about, a network partition. Now, this isn't just partition when they're talking about partition. It also can be delayed. So let's say instead of a strict partition where these are broken, let's just say there's delayed communication between these. That's also part of this network partition. It's just talking about the communication between these two nodes. So that's what they're talking about in network partition, is handling and dealing with this. Any questions on network partitioning? I think it's a pretty standard concept to deal with. Okay, so the last thing that we kind of very briefly mumbled over at the beginning, I apologize for that, was availability. I kind of got ahead of myself. I haven't done this type of stuff. And availability is defined as every request that is received by a node that isn't in an error state, is in a good state, must return a also not error response. So basically, these are like your high availability systems with eventual consistency, where you assume that there could be some dirty data. This is what a lot of people believe, but this is where we'll learn tomorrow where it's really important to dig into the details of what these things mean. And I actually agree with several things. A lot of people don't actually make two of these. You can actually have a database that is just partition tolerant, or maybe not even that. And that can be okay. It can be okay if your database is just P. That's fine. Now, the big misnomer that a lot of people have here is generally this is cap. So generally they'll say cap pick 2. And the thing is, you can't pick 2. You just can't do it. You can only pick 1. What do I mean? Well, the fact is, under network partition, you can't have consistency and availability. So if your network partitions in any way, you can't provide both availability and consistency. Can't do it. So you have to pick P. You have to pick network partitioning. So really, this is wrong. The real statement is cap pick A or C. So when talking about cap theorem, and when you're talking about your databases, you'll see AP or CP. That's like generally the nomenclature used, because everybody picks partitioning. You have to be able to handle this. And the reason you have to handle this is you have network switches that fail, you have HTTP, you have Ethernet cables, you have NIC cards, you have so much stuff that happens there. You can't guarantee a perfect network. And so if you picked availability and consistency and you had a network partition, you would have neither. So what does it mean in general when you have a CP? Let's talk over what it means when you have a CP. Now, again, we're talking about very generically, and these can change a little bit. And this is what we're going to dig into a little bit more on Saturday. So when you're talking about CP, oh dear. When you're talking about CP, how does your database react? So obviously you can have a network partition. So how does it react when there is a network partition? Because you want consistency. So in a network partition, not at all what I meant to do. Let's say that you had these 4 nodes here. We're going to have 4 nodes. That node is a bigger node than the other nodes. All right, there we go. All right, and this is our network partitioning. Now, again, we're going to get into consensus, and we're not talking about consensus right now, but this is our network partition. We don't know if let's say that we're getting a read here. Somebody is trying to read some data here, and we're having a write here. Now, the idea behind this is that in strong consistency, where you want that linearizability, you cannot know in this scenario that there hasn't been a write to the piece of data. And because of that, this has to fail under this condition. This has to return a failure. Now, be mindful of these things that I'm laying down, because these are the groundworks of why you need to move past CAP as a theorem. It is a true theorem, but you need to get past it as you'll find out, very few databases, if any, are actually CP or AP. By the definitions, very few. And I will guarantee you, here's something no one in the industry will tell you. Actually, absolutely everybody. When you run a database in strong consistency mode, it will 100% get slower. So if you could do 1 million writes and then you switched it over from AP to CP, you know, a lot of databases, especially the good ones like Aerospike, can actually run in either mode. And the thing is, if you could do 1 million writes through high availability, and then you switch it to CP, there is a lot more work the servers have to do to give you that strong guarantee, that linearizability. And because of that, there's a lot more work, and it just takes more network calls. And network calls are slow. Network calls are almost as slow as disk access. And because of that, it takes longer to do, and it's going to be a slower database. You're not going to hit the 1 million requests per second like your high availability database was doing. Just keep that in mind. Little nugget of information. Okay, so in strong consistency, this would return an error. So we're going to label this as CP. Now, we can take this and let's talk about what will happen in AP, or what you would expect to happen in AP. All right. In AP, the only thing that changes is this returns okay. It says, yeah, I don't know. This node could be down. This code could be offline. It could just be the network switch. Don't know. Don't care. This is the latest information. We're going to return a non-error response from a non-failing node. So this node might be failed. This node might be failed. That might be the partition. And so obviously these are going to return errors. Or just be unreachable. That could be the error if it's an actual network partition. And so they're going to return errors, but these are not going to return errors. These two, if you hit them, these are going to return something. So, CP consistency means that every read is going to either return the most current data, linearizability, or it's going to return an error. That's the guarantee that you want. This is the most recent data or no data at all. That's what you're getting. In AP, it says, I want the latest data that you have. And this doesn't guarantee linearizability, and that can be okay. This isn't a one is better than the other. This is understand what your requirements are, and is it okay to get a dirty read? There's a whole lot of ways to get a dirty read. Your database can provide strong consistency. It can provide linearizability here, and you can still get a dirty read because there's things like caching in your system that can provide those things and cause those things to happen as well. So dirty reads happen, and it matters on whether that's okay for your system or not. A lot of systems can tolerate a small amount of dirty reads. Can yours? I don't know. Okay, so that is CP and AP. The thing is, you can't have AC. You can't have AC. Cannot. You have to be warm in the data centers. No, the AC can't happen. And the reason is because then you can't survive a network partition. And if you can't survive a network partition, you either have to provide that your network will never have a problem. And if anybody has done any networking here, I think the guarantee would be that you have to tolerate network partitions. Period. You have to have a plan for tolerating network partitions, because they're going to happen. They're going to be slow. They're going to slow down, whatnot. And this is where we'll actually focus a lot on this network partition on Saturday. Oh boy, my internet provider just texted me. All right. So does this all make sense? All right, so an ad's going to start soon, so I'm going to take a little break while the ad is going, and then we'll talk a little bit more when we get back. XML. Wonderful. This was written a long time ago, 2004. Long time ago. about a minute left on the ad. About a minute left. How's everyone doing today? It's getting close. So next week, I'm out. But the week after that, we are doing consensus. So if you like this and think that this was interesting, like learning a little bit more about some of the more advanced topics, next is coming up is consensus. I think that you guys will really like it. Put a lot of work into it. We're going to talk about the different aspects of consensus, and then the couple different ways to solve consensus, the different styles of systems, and all while doing it, we're going to spend a couple hours a day working on writing a very, very rough implementation in Rust of the Raft consensus. So if you guys are liking this style of thing, there's nothing to write about CAP. I was thinking about writing but there's no implementation. It's merely a state of saying that you can't solve all three at the same time. You can't solve partitioning and you can't have a system that has all three of there. There's no Venn diagram with the middle. There's no amount of engineering that you can do to bring these things like this and get the Triforce in there. All of them require, you can only get two of these. And the problem with this one here, the problem over here is that if you do this, you can't. You effectively can't. That's the problem with this one, which forces you to pick these two because you can't have a perfect network. All right, so this is CAP theorem, and I know that I was super repetitive on this is linearizability, and I gave you guys this right here, which is a fantastic article on linearizability. But it's very important that you understand this is what CAP theorem is talking about when they mean consistency, not acid. And the reason this is important is because this is true. All this is true. And my next statement is understanding this is just the start. So the problem comes down to these are very narrowly scoped statements. I think linearizable databases are amazing and few and far between because there's a lot of ways that can go wrong. And we can dig into that if you guys like. But a truly consistent database in Brewer's term is few and far between. If you guys watch my database, tombstones are the worst when you're talking about databases and trying to delete data and making sure that data doesn't resurrect. Data likes to resurrect. It's amazing. It's a hard problem to solve to actually. You would not believe the number of issues that come up with data where data resurrects. Data likes to resurrect all over the place. It's a problem. But so deleting data is a whole thing in its own. It's very easy when it's just a single machine. The other thing that I want to clarify and make a point of, CAP doesn't handle non-distributed things. So SQLite, as we like to call it, but SQLite. Or SQLite. I think it's SQLite. But anyways, I always said SQLite. Is not a distributed database. It's not a distributed system. This system has no network partitioning because it's not distributed. Because it doesn't have networking partitions, you could actually have consistency and availability. If the node is available, it can also be strongly consistent. It can be ACID. So systems that are not distributed are not covered under these principles. It doesn't mean that these systems are bad. It doesn't mean that you can't use them. I think SQLite is fantastic, and it's a great place that a lot could start. It just means it's not covered under CAP theorem at all. CAP theorem is looking at distributed systems that are across networks and rely on each other to work. So we're talking about databases, like that's going to be the big one. Kafka would be another great one. Kafka is actually a database, as much as people hate me for saying that as my unpopular opinion. And that's what this is all talking about. So anything that's on a single machine or anything like that is not covered under CAP theorem. And that's really important, because a lot of times people get confused when they're talking about network partitioning. They can be like, oh, we can solve that by just running on a single machine. And you're right, you can solve it that way. But everything about Brewer's conjecture is about distributed systems. So just wanted to make those clear. All right, any questions so far about what we've talked about thus far? I have posted all of this content, I'm going to say my references. There's more that I've talked, read, and learned from. So this is not an exhaustive list of the places I have learned from, but these are some of the more impactful. Now, the ones that we're going to cover Saturday are basically why CAP theorem is the start of your understanding and not the end of your understanding. When you're talking about these systems, you need to talk about a lot of other stuff. Let's talk about network partition. I want to just spend a little bit of time helping you understand why, and then we'll dive into it deep on Saturday. Why these things? Let's talk about network partition. This doesn't cover out of memory. It doesn't cover servers going offline. It doesn't cover anything about consensus. It doesn't cover about disks filling up, server faults, corrupted data, or anything about that. It's just network partition. So it's a little finely scoped. Consistency, again, is, as we talked about, linearizability. But there's a lot of consistent databases that define it a little looser. You can actually have, now technically, they're not a consistent database per Brewer's conjecture. So if you're talking about Brewer's conjecture and how this became a theorem with mathematical proof behind it, if you're not talking about linearizability, you're not talking about Brewer's conjecture. But there's a whole spectrum of consistency that's available out there. And this is why when picking a database or understanding databases, it's really good to understand what that is and everything that's implied by those. It's really important for you to understand from your app's perspective. Do you need linearizable reads? Maybe if you're a financial institution, this is really important. And then picking your database is really, really important. You cannot maybe legally have a dirty read. Now, maybe if you're talking about your name on a social media site, maybe if you change it and then my neighbor goes and does a refresh on his web browser and it doesn't change my name for a couple of hours, it might be fine. It might be fine. There's actually an interesting concept here about dirty reads, on whether they're self-dirty reads or not self dirty reads. And by self, I mean, if I update it, do I get a dirty read? Because that's really annoying. If I change my name and then it's not changed in the UI, I'll think that it hasn't gone to the system. So there's actually two separate problems there, because you might not care about other dirty reads, but you would care about self dirty reads. That's a whole topic. So when you're talking about consistency and availability, the idea is that this is very, very narrow. And because it's so narrow, it's not really applicable. I know I said it's super important to understand, and this is why it's super important to understand. It's really important to understand what type of concurrency it is. It's not talking about ACID concurrency. It's talking more closely to linearizability. So that's what we're going to cover tomorrow, or not tomorrow, Saturday. Saturday at the exact same time, 4:30. And that's it for me today. Did you guys like it? Let me know. Leave a comment. Jump on the Discord. I thought more people were going to ask some questions. That didn't happen. So we kind of flew through the material. I have extra time. We can do something. We can talk about something. I have some more awesome references for next week. One of my favorite authors. I have two pretty favorite authors. I know that I bring them up a lot. I learned a lot of things from them. Would be Martin Klapman and Jeff Hodges. They actually disagree a little bit. And that's actually good. I love it when people can disagree and have a constructive conversation on it, because I've learned from both Jeff Hodges and Martin Klapman quite a bit. And they come at a little slightly different opinion. And I think they would have a really good, interesting conversation. I would love to have them on stream. Martin Klapman, Jeff Hodges, if you guys would like to join me on stream and talk about this in depth, you both know way more than I do. I will facilitate that. But we're going to talk a little bit about some of the things they have said, my thoughts on those topics, and why you have to dig a lot deeper into network partitioning consistency. Because again, there is entire spectrums on this, and CAP just doesn't cover all of them, and we're going to talk about them on Saturday. That being said, I'm also going to stream Saturday morning, so I'll probably do my normal stream on Saturday morning. So if you think of questions that you haven't had, you can ask then, and we'll cover them. This graph, this is a doozy. I have not been able to think of a better way of writing this for linearizability. And this is not a great one. I think a better picture exists in Martin Klapman's designing data intensive applications. It's not good. I always hated it when I read it. But I think it's better than mine. And then in a week and a half, well, actually, yeah, a little less than a week and a half, we do our consensus. We're going to talk all types of consensus. So the consensus is actually going to be much more in depth, because we'll have five episodes of that covering different topics of consensus. And the really great part about that right then is that you're going to see different aspects. We're going to cover all the way from like blockchain style consensus. I like to refer to it as untrusted consensus versus trusted consensus, like your Raft and Paxos consensus. We're going to talk about the problems that they try to solve and how they solve the problems. And we're going to look at a little bit of the differences that they take, the different approaches they take to coming to consensus when talking about those distributed systems. CAP theorem is really important on that because you have to deal with consensus with network partitioning, and how you deal with availability when that happens. What we're going to do in the second part, so the first part's going to be all theoretical, no code. The second part, we're going to actually implement Raft, a consensus algorithm that powers etcd, which powers Kubernetes. Now, ours isn't going to be a full implementation. We're going to try to skate through with just the bare minimums to just learn better the very basics. I've never actually implemented Raft before. So that's going to be a ton of fun and happen in roughly 1.5 weeks. I think it starts, I want to say it starts Saturday, a week from Saturday. So yeah, those are going to be longer streams. So all right. Any other questions? In January, I think I do plan on making either 2 little videos or 1 longer video out of this. Yeah. So you can expect to see that. Tomorrow or next week, I'm out, but I do have my database index video that's going to drop. I'm going to publish whatever. I'm working on some animations, and I've just set the deadline of Saturday. I'm done with whatever animations I can get done by Saturday, and we're going to move on, and that's the video you're going to get. So hopefully you guys like it. Give it a watch, and let me know if you like the animations. I worked on it a little bit, so yeah. All right, well, if nobody has any questions, check out the links that I left. Saturday, I will be leaving more links for you all to check out about some of the stuff that Jeff Hodges and Martin Klapman have come back and not retorted, but like basically their takes on the CAP theorem and what it means to us. And we're going to talk it a little bit more in depth. Actually, we have more content for that. One's going to be a little bit longer, even if nobody has questions, because we're going to talk about what it means practically as well. We're going to talk about the struggles that CAP theorem has. Like I said, it's very narrow in its scope, very narrow. We're going to talk about the struggles in its full scope, and then we're going to talk about practical applications. I have a whole list of databases and the different ways that they deal with those, and some of the things that you can start to think about when designing your system, understanding what it needs, and what the CAP theorem means to you when evaluating these. Hey, how are you doing from YouTube? It's good to see you. I'm glad you were able to join. Do you have any questions from the content we covered? I'm going to call you, I don't know how to pronounce your name, but it's good. We were just wrapping up. This is the first video on CAP theorem. We have a second one coming up on Saturday, roughly the same time, 4:30 Eastern Standard Time. So if you'd like to join that one, that's basically, today was just an overview of what CAP was. And on Saturday, we're going to really dig into why we need to move beyond CAP. Why CAP isn't the end all be all. It's a really good starting point. But it, yeah. Oh, well, you know what? I would say if you liked what it was, but you wouldn't know, the video is on YouTube and stays up there. So all of the past streams are up there. So you go check it out. You can start the recording over if you like. You can't ask questions, unfortunately, because it's a recording at that point. But there is a Discord channel that you can find. And, I don't know if that's linked in the video, let me Let me get you the link to the Discord. We have a whole community. The other awesome part, if you go and rewatch the video on YouTube, is it has the chat history in there. So during this, I actually released a lot of the references that, you know, I've learned from in the past on this topic. So you can also go and check those out. And I'll be doing the same thing on Saturday. Here's our Discord channel. Bunch of nerds talk Kubernetes, distributed systems, databases, software engineering. I also have my main YouTube channel, which is I don't even know what this is. All right, well, you know what? Let me talk you really quickly over what we covered today. So today and Saturday, we're talking about CAP theorem. CAP theorem is something that was Eric Brewer talked about. It was called Brewer's conjecture. And he talked about this AP and CP and basically CAP. Consistency, availability, and tolerance to network partitions. That's where the CAP theorem came from. And you kind of get a diagram that looks like this. And this is in reference to distributed systems. And you get a diagram that looks like this. You can't have all three. You can have two. Later, Seth and Nancy actually basically proved CAP theorem. And this is when it became a theorem, CAP theorem, hence CAP theorem, because it was Brewer's conjecture. And we get into this. And so basically what this is saying is in a distributed system, you can only provide two of the three. You can't provide all three. Now, this is a little bit of a misnomer because you have to provide network partition failures. Because in a distributed system, you will have partition failures. You will have network switches that die. You will have switches that do weird things. You will have slow packets. You will have NIC cards that die. You will have nodes that fail. You will have network partitions is the end all be all. Unless it's not a distributed system. But we're only talking about distributed systems, so that doesn't really enter in this case. So then there's the understanding what consistency means, which it really means the linearizability, which again, I gave a link to this, which is a really good, what is linearizability? Basically, it's a very stringent form of consistency that says that if two people read from the database and they hit two different nodes, they have to return the same value. I'm simplifying it a little bit. There's really, I explained it with this diagram, which is not a great diagram. You can go back and watch, but that is the consistency that Brewer's conjecture requires. And then availability is effectively, if a node is available, it will respond with a non-error. So if it's not in an error state, it will respond with a non-error error response. So yeah. So hopefully by the end of today, after you watch the video, you'll know what CAP theorem is. That was the idea. If I didn't do that, you should leave a comment. Let me know why you don't know what CAP theorem means. Yeah, Saturday, we're going to dig into why you need more. There is my main YouTube channel. I'm going to be making videos off of this, so I do really want all feedback because I'm going to make videos based off of this content for January. So in January, you should get 2 small videos on CAP theorem, and I do want the feedback because if there's something that's confusing that I didn't explain well or that you have further questions on, others may as well, and I'd like to include that feedback in those longer form videos. Another thing, I'm going to call you Gome. I don't know if that's how you pronounce your name, but another thing that's really, that's going to be a lot of fun is a week from Saturday, we start our consensus. You might have heard of a consensus from things like blockchain technologies talk a ton about consensus, where there's proof of work, proof of stake, or proof of, there's a lot of proofs. Anyways, they talk a lot about consensus, but there's also consistency in things like Kubernetes. So Kubernetes is powered by etcd, which uses the Raft consensus protocol. There's also Paxos and Paxos-like algorithms. Aerospike notoriously is a Paxos-like algorithm that reach consensus. This a way for you to have strong consistency in a redundant system. So a week from Saturday, we're going to start digging into that. And that is going to be actually a little bit more in depth, because we're going to have a little hour-long demo like we did today, a little hour-long thing. Then we're going to actually get into the code, and we're actually going to program a very, very light version of Raft. It's going to be a very simple version of Raft, but it's going to be a version of Raft, hopefully if we can do it. So yeah, we'll have like an hour-long workshop, and then 2, 3, 4 hours of implementing some of the ideas in a consensus reaching system. So all right, well, that is it for me today. That was all that I was planning on working on. So if you have questions, if you're watching this in the past, join the Discord and let me know those questions. If you're, it would be very helpful to me to make really good videos in January for people to watch and understand better. My goal is to help us all learn something new. And so I hope that you learn something new. I hope I learned something new, and thanks everybody for joining, and I will see you guys Saturday. I'll stream twice Saturday, once in the morning, once in the evening like I did today, and hopefully we'll learn something new, like why cap is not great, but it's awesome. It's awesome, but you got to move beyond it, beyond cap. All right, see you guys in a couple days, 2 days, not tomorrow.